Welcome to APP Daily, Topic 3.1, Intermolecular Forces. In this video, we will focus on the nature and relative strength of intermolecular forces. I'm Kristen Cacciatore from Charlestown High School in Boston. So we're going to start off by contrasting intramolecular forces and intermolecular forces. So an intramolecular force is essentially a covalent bond. It is an attraction that holds atoms together within a single molecule. An intermolecular force is an attraction between atoms that are on different molecules. So it's represented here by the dashed red line. All right, so how are intermolecular forces formed? Well, water molecules, for example, are polar. So we know there's a partial positive charge on hydrogen, partial negative charge on oxygen. And that means that the negative oxygen is going to attract the positive hydrogen from another molecule. And that's a Coulombic force. It's an electrostatic force. So it's just like a covalent and ionic bond, but IMFs are generally weaker than covalent and ionic bonds. Okay, so let's talk about one particular type of IMF, which is called a dipole-dipole interaction. These occur between any two polar molecules. They can be attractive or repulsive, but generally molecules are going to orient themselves so as to maximize attraction, minimize repulsion. And the strength of these dipole-dipole forces is directly related to the magnitude of the dipole within the molecule. Common examples of molecules that experience dipole-dipole forces: carbon monoxide, ammonia, and dichloromethane. All right, think about this. Have you ever wondered what fish breathe? Well, they actually breathe O2, the same thing that we do, but they need to get it from underwater. So nonpolar oxygen molecules actually dissolve in water, which is polar. Fish can then take in the O2 from the water. But we want to know as chemists, what attracts these molecules enough to keep them in solution together? Well, it's a dipole-induced dipole interaction. When a dipole of water approaches the nonpolar O2 molecule, the electrons in O2 are repelled by the negative part of water, and O2 is forced to have a dipole. In this situation, the usually nonpolar oxygen molecule temporarily becomes slightly polar because of the effect of the water. And this dipole depends on the orientation and the proximity of the water molecule. If the water molecule moves away, then the dipole in oxygen ceases to exist. And this type of interaction is always attractive. How about interactions between two nonpolar molecules? We've already talked about polar molecules, then we get dipole-dipole, or between a polar and a nonpolar, we get dipole-induced dipole. Can two nonpolar molecules interact? Like oxygen, can oxygen molecules interact with each other? Or bromine molecules interact with each other? Yes, they can. Let's take a look at how this happens. So here's two bromine molecules. Even though bromine is nonpolar, electrons are still randomly fluctuating inside the molecule. They move around. And these fluctuations produce temporary dipoles. And when the temporary dipole of one bromine approaches another bromine molecule, it induces a small dipole in that second molecule. And then you end up with partial positive and negative parts to these two molecules that are attracted to each other. So we get these induced dipole interactions, which are called London dispersion forces. That's a synonym. Or LDFs, they're sometimes abbreviated. All right, so we can see that on our nice diagram there on the left. London dispersion forces, all molecules exhibit them, even polar molecules. They're the primary type of intermolecular attraction between nonpolar molecules. And this is very important. The strength of LDFs depends on how easily the electrons can disperse inside a molecule. The larger the electron cloud, the more polarizable it is, and the greater the strength of the LDF interactions. LDFs, therefore, in large molecules can be quite strong. All right, let's compare three nonpolar molecules, fluorine, chlorine, and bromine. Notice that as you go down here, the molecules get bigger and the boiling points get higher, which indicates that they have a higher boiling point as we go down here. So the larger the molecule, the more polarizable the electron cloud, resulting in stronger LDFs and therefore a higher boiling point. Let's compare two nonpolar isomers, butane and 2-methylpropane. So they have the same chemical formula, but a different structure. Notice that the butane boiling point is slightly higher than the methylpropane boiling point, and that is because butane, with its linear shape, has a larger surface area, which allows for more interaction between molecules, and thus higher LDFs. All right. And how about comparing the strength of IMFs in two different substances? Well, we've got Cl2 and HCl in our table. We need to notice the heat of vaporization data and the dipole moment data that were given. The problem asks us first identify the IMFs present in each substance, and then second, explain the difference in heat of vaporization in terms of relative strength of IMFs. Well, first of all, we notice that Cl2 is nonpolar, HCl is polar. So Cl2 has only LDFs, but HCl has both LDFs and dipole-dipole interactions. The second part is a little trickier. Notice the heat of vaporization for chlorine is larger, and therefore it has more IMFs, even though it has only one type of IMF. So that means that the LDFs in chlorine are greater than the LDFs plus dipole-dipole interactions of HCl. Okay, now let's do a practice problem. Two different Lewis diagrams, ethane and methanol. They have the same molar mass. One of these two molecules is a liquid at room temperature. The other is a gas. We have to decide which one based on their structures and intermolecular forces. Well, stop the video here and try the problem on your own. Then we'll go over it. All right, so ethane is nonpolar, so it has only LDFs, and methanol is polar, so it has both LDFs and dipole-dipole interactions. Because their sizes are comparable, the LDFs are similar, and methanol will be the liquid because it's got the additional dipole-dipole forces. Thank you for watching.